Thank you, Bala, for that kind introduction. And thank you, Rajesh, for inviting me, for the mementos, and for this opportunity to talk to all the young people here, many of whom are probably just starting their astrophysics careers or physics careers in many of your cases here. I'm going to share with you an exciting field, black hole astrophysics. It's an old field. Astronomers have been studying black holes, or what they thought were black holes, for many, many years. It's all been done through electromagnetic radiation, and I'll touch just on a few highlights in that area. But the real recent activity and excitement is from gravitational waves. I'm going to say nothing about that in my talk, because following me, we're going to have two talks on LIGO results, especially the recent announcement of a second object that they have detected. Okay, so to make sure that everybody knows what we are talking about, I got one slide to remind you all what a black hole is. So the black hole is something that was predicted by Einstein's general theory of relativity. And in fact, the first black hole solution was obtained within weeks after Einstein presented his theory. This was the solution discovered by Schwarzschild. And since then, other solutions of black holes have been found, but it's something that came from a theorist's mind, and it's wonderful that now we know that these things are real and we see them all over the universe. So what is, in very brief detail, a black hole is when an object has so much self-gravity, its own gravity, which is compressing it, is so strong that the matter is unable to hold itself up, and everything gets squeezed down to a point. So this has got finite mass here, this little dot, but it has zero volume, zero radius, zero everything else, but it's just got finite mass, infinite density. Okay? So all the mass has been crushed down to a point, which is called the singularity. And this is different from any other object that we study, because everybody else has got a finite volume, finite density, etc. So this object doesn't really have a surface. Instead, what it's got is a kind of a virtual surface. It's called an event horizon. So it's some kind of, think of it as a one-way membrane. So stuff can flow in from outside to the inside. But once something goes inside, there's no way to escape. And the way people like to say this in the popular language is, once you've gone inside the event horizon, even if you shine this laser pointer, this beam is going at the speed of light, even that light cannot escape. You shine this pointer, the light will fall down into the singularity. So this is kind of a real boundary, which is separating parts that are visible to the outside world from parts that are just not visible. Okay, so that's the event horizon. What is the actual radius of this horizon? Here is the formula. It's named after Schwarzschild, the first black hole discoverer. So this is the Schwarzschild radius. It's given by 2gm over c squared. G is the gravitational constant. M is the mass of this object, the gravitational mass that you will measure at a distance. C is the speed of light. And in practical units, it's about 3 kilometers for an object with a mass equal to the mass of the sun. It's proportional to the mass. Okay, so this is a black hole. Now I have to make a disclaimer here. This is what I would call a classical black hole. It is a black hole that comes from general relativity, and general relativity is a classical branch of physics. You won't see Planck's constant anywhere. So for instance, the Schwarzschild radius involves gravitational constant and speed of light. So it's gravity, it's relativity, no quantum mechanics, okay? So these black holes I'm going to tell you about are all classical objects. Meanwhile, there's a huge body of work being done in physics studying quantum aspects of black holes. I'm not an expert in this, so I have no business telling you anything about it. Plus, it would be a whole another talk or multiple talks. You should get somebody else to tell you about it. There is a lot of very interesting stuff related to quantum gravity. So for instance, this famous work, Hawking radiation, the information paradox, and there are many, many interesting things. String theory is all coming from this part of gravitational physics, and I'm going to leave that completely aside for my talk today. Okay. Now, the concept of this singularity, infinite density, the concept of a horizon, the one-way membrane, nothing can get out, all these are very new and weird. And physicists have taken a long time getting used to even these ideas. And to tell you the truth, Einstein himself never really thought black holes are real. It's a beautiful consequence of his theory, but he thought somehow physics would find a way to avoid it. So for a long time, nobody thought these things are anything more than a theorist's toy model. But what we now know is they are present in the universe, and not just present, they're present in huge numbers, okay? You can't look anywhere without seeing a black hole somewhere out there in the sky. Basically, there are black holes in the universe in two categories. There are so-called stellar mass black holes. These typically have masses between 5 and 20. This is the symbol for the mass of the sun, solar masses. And as we now recently know from LIGO, it goes up to at least 30. So, but there is a range which is centered around 10 solar masses where we have lots of black holes. These are all called stellar mass black holes. And then there's something called a supermassive black hole, which is a completely different population. Masses between 10 to the 6 and 10 to the 10 solar masses. So what do we know about these two populations? Firstly, let me tell you, rough estimate is these stellar mass black holes, the guys in this mass range, there are probably more than 10 million just in our own galaxy, okay? And every galaxy has got 10 million. It may well be 100 million, okay? It may even be a kind of an underestimate, okay? But it's a huge number. These guys are formed naturally as part of stellar evolution. I don't want to go too much into the astrophysics of it. We think we know how these objects form. They form when stars die. Most of them are invisible. We have no way of finding them. But a small subset of these black holes happen to be in binary systems. So in this picture here, the black hole is here, and it's a second star, companion, which is close to it, and the two of them are in orbit around each other, which is shown by the movie up there. So think of it as a binary, gravitationally bound stellar system. And in the particular systems I'm talking about, the two objects are so close together that gas is able to transfer from the companion star to the black hole. So it flows here. Because of angular momentum, it goes into orbit, and then it slowly spirals down, reaches the center, and while the gas is spiraling in, it's falling into the gravitational potential of the black hole. So essentially, it converts that potential energy into other forms, including heat. So this gas becomes terribly hot by the time it reaches the center, and it radiates X-rays in these systems. And we see them as bright X-ray sources, and they're called X-ray binaries because they're obviously binary systems. So I would say that we know about maybe in our own galaxy 50 of these objects, maybe 100, I don't think it's 150, and we got a number of others in other nearby galaxies, but nothing like the whole population, 10 to the 7. All the others are dark. Okay, then there are the big ones, the so-called supermassive black holes. And in contrast to the stellar mass black holes, these, one per galaxy. One big black hole that sits right in the middle, in the nucleus of the galaxy. Our own galaxy has got one big fellow right in the middle. Virtually any galaxy you look out in the sky, if you look in the center, and if you have enough sensitivity to tell what is there in the center, you find a supermassive black hole. And as I said, that's the mass range, 10 to the 6 to 10 to the 10. These objects, again, often have gas disk around it. So this is gas just coming from the galaxy, just in ordinary so-called interstellar medium, goes into orbit, spirals in, and because of the way the parameters work, for these systems, when the gas comes close to the center and becomes hot, it radiates in optical and ultraviolet, whereas these guys radiate in X-rays. It's just a consequence of the different mass. So we see these as bright optical and ultraviolet sources in the centers of galaxies, and these are called active galactic nuclei, etc. But in both cases, the way we find them generally is through the radiation of this gas flow that's coming in. The black hole itself is dark, okay? But the gas that's coming in is bright, can be awfully bright, and we see them as these bright optical or X-ray sources. Okay, So now here's the big question. How do we know they are black holes? Okay? So I'll tell you the astronomer's working definition of a black hole. It will not satisfy anyone in this room, I think, but I'll tell you, this is the working definition. Definition is, firstly, your object must be very compact. That is to say, you must be able to get some proxy or measurement of the size of the object, and it should be comparable to the Schwarzschild radius. You'll never be able to measure precisely to say, yeah, it's exactly equal to Schwarzschild radius. But if it's within a few or 10 Schwarzschild radii, we say that it's an ultra-compact object. So that's the first requirement. Now that alone is not enough, because we have a counterexample called the neutron star. The neutron star is a dense, neutron-rich spherical object, which is another product of stellar evolution. And that guy is not a black hole. It has a surface. It's got a finite density. It's got everything finite. And it's got a radius that is only a few Schwarzschild radii. So we have to now distinguish between the neutron star and the black hole. Here we use the second criterion. Namely, we know from theoretical models that you cannot have a neutron star more than about 3 solar masses. Just as white dwarfs have a mass limit, the famous Chandrasekhar limit, neutron stars have a mass limit. And you go above that limit, it will not survive as a neutron star. It will collapse and become a black hole. So if you find a compact, say an X-ray source, and you get some idea of its size, few Schwarzschild radii, and you measure its mass, and you find that the mass is greater than 3 solar masses, then the astronomer is happy. This is a black hole. It's done. The problem with this is, if you go back to what I said in my first slide, how do I describe a black hole? I didn't tell you that a black hole is an object that is not a neutron star, right? I told you a black hole is an object with a singularity and a horizon and all that. Finding evidence of these things is much, much harder. There is actually some work, which actually my group has done, I'm not going to say anything about it, trying to prove that what we call black holes really have horizons, that they are different from the neutron stars. There are some things you can do. It's never foolproof, but it's pretty good. Okay, so I'll keep that for another story, some other time. So for right now, let's just say this is where we are. We take this as our criteria, and I'll continue on. We'll pretend that these are all black holes. Now, LIGO is a different story. We'll find out later. I think they are pretty close to proving that we really have black holes. Next, very interesting concept I want to introduce here. Black holes are the simplest objects you can possibly think of within classical physics. In classical physics, we all say, yeah, let's imagine that the object is a sphere, right? Maybe a cow, right? We have the spherical cow model. That's why you're trying to model the cow. It's too complicated. It's got a body, head, eyes, all that. I don't want to do all that. I'll model it as a sphere, because the sphere is beautiful. All I need to know is its mass, its size, and that's about it. A black hole, you don't have to make such an approximation. Turns out that a black hole is as simple as the spherical cow. In fact, according to all the models of black holes that have been obtained by solving Einstein's equations, we know that the only possible parameters that a black hole can have are mass. So this is how much gravity it exerts on other objects. How much angular momentum it has, J, some kind of a spin. And in principle, it can have electric charge. So if you take a black hole and it happens to have some electric charge, that's a fundamental conserved parameter associated with the black hole. And according to theory, this is it. This is a complete description of every black hole. If you give me these 3 numbers, you have said everything possible about the black hole. It's a very, very smooth, featureless object. It has no additional detail of any sort unless you go to the quantum regime. And since I'm leaving out quantum mechanics, within classical physics, this is the whole story. People like to call this the no-hair theorem, which comes from this statement: a black hole has no hair. The idea being, if the black hole had any hair sticking out, you would need lots of numbers to describe the hair, right? Where is it attached? How long is it? How thick is it? What color? All that stuff, right? A real black hole has no hair. No hair, no bumps, no mountains, no nothing, okay? It's just this sphere, and therefore it only needs a few numbers. Okay, so these are kind of the general things that I wanted to introduce about black holes. So let's talk about astrophysics. So following on from this slide, I said there are 3 parameters for a black hole: mass, angular momentum, and charge. And I put a dash here because astrophysical settings, we don't expect a lot of electric charge on a black hole. It may have some charge, but it won't be dynamically important, okay? It'll just be trace charge. So in the astrophysics community, we never at all worry about this parameter. Our black holes have only 2 numbers: mass and spin. So what I'm going to describe is how people measure these 2 parameters for the candidate black holes that we have. Then I'm going to go, after discussing these 2 topics, talk a little bit about this thing called the Penrose process, which is a beautiful physics concept, but also apparently has some contact with astrophysical phenomena. So I'll say a little bit about that. There is a 4th topic which I'll only just touch on because I'm going to discuss this in greater detail next week in an academy talk at IISc campus. I don't want to spend time on that here today. So mostly today, these are the 3 topics I'm going to discuss. Okay, let's start with mass. How do we measure the masses of these black holes? Mass is actually easy, okay? Measuring mass is something astronomers have been doing for a long time, and it all goes back to just Newtonian physics, freshman physics that we all learned. So I'll just remind people, if I had a mass m and I put a test particle at some radius r, and let us for simplicity assume it's a circular orbit, then we know we can balance the centrifugal acceleration with the gravitational acceleration, simple relation like this, and by rearranging, you get the formula like this. The mass of the central object is equal to v cubed p over 2 pi g. V is the velocity of this particle in its orbit. P is the period, how long it takes to complete one orbit. And I'm sure we have all done this calculation at some point. We know the Earth is going around the sun at 30 kilometers per second. Earth takes 1 year to go around. If you plug in these 2 numbers into this formula, you will measure the mass of the sun. 2 times 10 to the 33 grams. And this is something you can do without actually going to the sun. You don't have to go take a weighing machine there. Just looking at the Earth's orbit, we get the mass of the sun. So when we have an X-ray binary, we do the same thing. Here is my black hole. Here is my companion star. These 2 guys are going around each other. It's almost like my test particle. In fact, in some of the systems, this second object, this companion star, is much lighter than the black hole. And then it's almost a perfect test particle. But more often, it's not a perfect test particle. You have to account for the mass of the second guy. But we know how to do that with Newtonian physics. But essentially what you do is you take one of these X-ray binaries. This center is producing all the X-rays. But for measuring the mass, you don't look at that. You look at the companion star. You look at the star as it goes around. You look at the spectrum of the radiation, and you measure the Doppler shift. So when the star is coming towards us, the whole spectrum will be blue shifted. When it's going away, it will be red shifted. So you measure the velocity of this star as it goes around. The period, of course, comes automatically as a bonus. The moment, you just measure how long it takes to repeat the pattern once. And so you get both V and M. And, you're in business, you got a mass. 2 complications. One is, what you measure is not the true velocity of the companion. You're measuring only the line of sight velocity. The real velocity is in some orbit that's going like this, and you measure only its projected velocity. So you have to make a correction for the inclination of the orbit. And this is a little bit tricky, because you don't resolve this. You can't actually see the orbit. So you don't know what the inclination is. So we have to use some other astronomical signatures. Okay? Again, without going into details, there are ways of doing it. You can get a decent idea of the inclination of the system, and you put that in. The second complication I've already mentioned, namely, this is not a real test particle. It's a finite mass object. So you have to allow for the reflex motion and things like that. Very straightforward calculations. So this is how we measure masses of X-ray binaries. Okay. People have done this now And there are something like about 20 or to 25 really good mass measurements for black holes. And there is an equal or maybe larger number of measurements for neutron stars. And this plot is just to show you how neatly the two populations divide out. So you just take all the measurements and bin them, and then you plot them versus mass. This is something like a probability distribution of mass. And all of your neutron stars are sitting here. In fact, it looks like the neutron stars pretty much die above about 2 solar masses. The theoretical limit is 3 solar masses. But it looks like in reality they cut off 2 or maybe 2.1, 2.2. And all these black hole candidates that I've talked about, they sit here. Kind of they peak probably around 7 or 8 for the ones that we have seen. There's a long tail. We used to think the tail goes up to 15 or 20, but after LIGO's first discovery, we know it goes at least up to 30 and maybe beyond. But the fact that there is a gap here is rather nice. It shows, at least it kind of makes it plausible that this is a different kind of object from that. It's not a continuum. That's all I can say. Let's look at the supermassive black holes. How do we measure those masses? Again, Newton. Newton will tell you how to do it. And this is some of the most beautiful observational work that's been done in the last 20 years in astronomy. So let me explain what's going on here. So this is a kind of a movie representation of real data. Up here is time. Okay? It shows actually, it starts in 1992. So that's when the observations were started, goes on and on and on. What are we seeing? These are infrared astronomers who looked at the center of our galaxy. So in the center, there's a black hole. So they look at the center of our galaxy, and they go again and again and make a picture of what's going on in the center. So each of these dots here is a star. So you just make one image of the star in 98, 99, 2000, and what you find is that these stars are all running around. They're not just sitting there at rest. These are stars in the center of our galaxy, but they're all going around in orbits of some sort. And the interesting thing is they're not going in straight lines, right? Newton said in the absence of any force, things should go in a straight line. Look at this star. This is the famous S2. Look at that. Doing that, comes down here. In fact, it's finished more than an orbit by now. And there are many other stars like that. The beautiful thing is you can take the orbit of this guy, because you now have position versus time. You can fit it to a Keplerian elliptic orbit. And you can say, what do I need to produce this Keplerian orbit? What you find is you need some mass sitting at the location of that plus with this much mass. 4.5 10 to the 6 solar masses of gravitating material has to be present at that location. It's dark. You don't see anything there, okay? It's completely dark. But these stars know that they're there. It's there because all the stars are going in orbit. This is data from another group. There are more stars here. And what I can say is by now there are some half a dozen or more, maybe by now it's 10 stars, for which you can fit detailed orbits individually. And all of the stars' orbits require one dark mass at exactly the same position with exactly the same mass. It's just a beautiful confirmation of the existence of a compact gravitating object right at the location of the plus or the star in these two images. This is our own galaxy. Okay? This is the best mass measurement that anybody has made for a black hole. Similar work has been attempted in other nearby galaxies. You can't quite do as fine a work as this. But there are nice techniques that people have developed. And without going into details, there are mass measurements for black holes in, by now, probably about 50 nearby galaxies. So we've got mass measurement. This is where the statement I made, that every galaxy has a black hole. This comes from the fact that the 50 nearby galaxies for which we can do this measurement, virtually every one of them has shown a dark, compact object with mass in the range 10 to the 6 to 10 to the 9. So this is how we measure mass. So one of the two parameters of a black hole. Yeah, please. It could be a clump of dark matter, but then you can ask, what are the properties of that dark matter? People have models called boson stars. Okay? If you choose the mass of your boson suitably, you can make a non-black hole but gravitationally bound fuzzy object compact enough. Compact enough to fit inside these orbits. That's not a problem. But it turns out that for this black hole, we have other evidence that the object is much more compact than the orbit. The orbit, I should mention, since you've asked, at the nearest point, this SO2 star is still about 1,000 Schwarzschild radii from the black hole. It's still quite far. That's why, just Newtonian physics is enough. But we have other markers which come down to a few Schwarzschild radii. Then you're really pushed with this boson or fermion or whichever particle you want to choose. It has to be a very precise mass. And the problem then is that same mass will not work for some other black hole because we have a range of masses. So when you put that requirement, none of the simple models will work. Yeah, but absolutely a fair question. How do we know it's a black hole? This is still an open question in my mind. Okay, let me talk about spin. Somebody will give me warning about time. Half an hour to go? Okay. Measuring spin. Mass was easy. Spin is extremely difficult. So let me tell you why. Let's go back to Newtonian gravity, okay? So in Newtonian gravity, I have the sun. Let's think of the sun as a nice spherical object. Sitting out here on Earth, I can measure, as I said, the mass of the sun. Because that gravity I feel, it's a long-range force. If the sun is spinning, I can't tell whether it's spinning this way, that way, or spinning at all, because the gravity doesn't directly tell me anything about the spin of the sun. Newtonian gravity is completely determined by only mass, or mass density. Spin makes its appearance only when you go to general relativity. There it turns out that spin has its own gravitational effects, but they are all short range. You have to go close to a compact object before you can see really, any strong effect due to spin. If you want to measure it at large distances, you need extraordinary precision, which people do. For instance, they try to measure in the vicinity of the Earth, but those are different kinds of experiments. The kind of astrophysics I'm talking about cannot do those measurements. We have to go right close to the black hole to see any evidence of spin. Spin will come through a quadrupolar distortion. So that's different. That's just, I can have a quadrupolar mass without spin, and I can have a quadrupolar mass with spin. If they have the same shape, I can't tell the difference. In GR, you can. GR, the angular momentum will have a frame dragging effect, which the non-spinning distorted object will not. So yeah, it's actually an extra term. It's a different term, T phi, for the specialists. Okay, spin. So as I say, it's all close to the black hole. So we have to use some kind of tools near the black hole in order to measure spin. Fortunately, we have such an object. We have the accretion disk, right? If you remember the pictures I showed you, there's the accretion disk. Gas starts off at large radius, but it keeps coming closer and closer, and finally, in fact, the gas disappears into the black hole. So if only we knew how to model that gas properly, the part of it that is very close to the horizon will tell us, if we are clever enough, will tell us what the spin is. So that's the idea. So I'm going to mention one very basic result from general relativity about orbits. If I have a compact mass and I put a test particle in a circular orbit, we already saw this, Newton tells you how to solve for that. Now when you look at that Newtonian result, you will be able to find a solution for the orbit at any radius you please. Newton's gravity has no scale. So you can put the test particle close, far, only thing that will change is the velocity. This is not true in general relativity. General relativity, if I take a compact mass and I put a test particle at a large distance, it will behave exactly like Newton. As I come closer and closer, I'll start seeing deviations from Newtonian gravity. Well, it is a different theory, but the biggest qualitative change is I'll come to a particular radius called the ISCO, innermost stable circular orbit. And when I come to that radius, if I try to go anywhere further in, the particle will not be in a stable orbit. It becomes unstable. So outside the ISCO, I can put a test particle, it goes round and round. It'll do it forever. Inside the ISCO, if I try to put it in a circular orbit, it'll just fall into the black hole because it's unstable. So there is a nice characteristic radius, the ISCO, which is telling you about general relativistic phenomena. Wait, I'm giving a talk, right? You'll see it. Okay, so for a non-spinning black hole, it is at 6 gm over c squared. And the nice thing is it does depend on the spin. So if I have a black hole, if I put spin parameter A, this is a parameter that tells you how fast a black hole is spinning. 0 means non-spinning, 1 means maximum spin. Okay. Let's not go into the details. So there's a range that the spin can have. The radius of the ISCO goes all the way from 6 to 1 gm over c squared. So it's a nice factor of 6 change in the radius of the ISCO. So if only we could measure ISCO, and Haridas asks, how the hell are you going to measure the ISCO? It's so far close down to the black hole. Just wait, here it comes. Here's the picture, okay? Qualitatively. I told you there's an accretion disk. What is the accretion disk doing? It's taking gas at a large radius, and the gas is going round and round and round and round, and as it comes down, 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 as I said, it's producing heat, gets brighter and brighter and brighter, and it's radiating. And the gas, lives for a relatively long time at each radius, and it converts the potential energy into radiation, which we observe, until the gas comes to the ISCO. Once the gas comes to the ISCO and crosses the ISCO, remember, there's no stable orbit. This gas will fall in on a dynamical time, millisecond, in the case of a stellar mass black hole. So in 1 millisecond, it's gone. So what we expect for our accretion disk is, there will be radiation from all over the disk. It'll get brighter and brighter towards the center. It'll be brightest right here near the ISCO, and then it'll become very dark. May not be black, but it'll be very much dimmer. So there'll be a dark region in the middle because there is no stable orbit there. That's why the gas is falling in. And if you have a non-spinning black hole, this black region will be big because the ISCO is 6 gm over c squared. And if you have a very rapidly spinning black hole, this dark region will be very small because it's 1 gm over c squared. So all you have to do now is measure the size of this dark hole in the disk somehow. And if you can measure it, then you're in business. You can calculate the spin, estimate the spin. So that's the game, okay? Still, it doesn't answer how do you do it, because let me tell you, maybe some of the young people might be confused. You may think that these are actual pictures obtained with a telescope. These are artists' pictures, okay? No telescope will ever get you such a beautiful image, because these things are so small, okay? So somebody has painted this. What we actually see in the telescope is just a point of light, which is producing X-rays, optical, whatever. Now you have to interpret that somehow. So how do we get the radius? So here is this beautiful little trick that all astronomers know about, measuring the radius of a star. All those stars in the sky, virtually none of them has ever been resolved, even with the biggest telescope. They're all points of light. And yet we know the radii of all of these stars. How do we do it? Here is the simplest way you can do it. You use the fact that a star is a pretty good black body source. The spectrum of radiation that comes out is, to a good approximation, black body radiation. So here's a formula. The luminosity of a star is 4 pi d squared f. So what do I mean by f? Is the flux that I receive from this object. So I put a photometer, I just measure how many ergs per centimeter squared per second is coming from the star, multiplied by 4 pi d squared, where d is the distance to the star. Assuming the star is radiating isotropically, this of course is the luminosity. But now I'm telling you that the star is a black body radiator. Knowing that, I know that the luminosity should also be equal to 4 pi radius squared, that's the area of the star, multiplied by the black body flux, sigma t to the 4. Sigma is the Stefan-Boltzmann constant. T is the temperature of the radiation. That's an easy thing to measure, because all you need to do is to look at the spectrum. Spectrum, where it peaks, is 3 kT or whatever, so you've got the temperature. So these are two really, I would say, trivial quantities to measure, so long as something is a good black body. So you've got a nice little relation, and when you rewrite it, you will get a formula like this. The radius of the star is d times square root of f over sigma t star to the 4. You never had to resolve the star. You had to measure the flux, easy. Measure the temperature, easy. Measure the distance, not so easy. This is the one that holds you back. But there are methods for measuring distances, and once you've done it, you know the radius of the star. So you kind of play the same game here. So here is my radiating object. So again, very kind of a very general description. Even though my accretion disk is radiating everywhere, the bulk of the radiation is coming from some effective area down here near the center, what is drawn here in white. So if we take our X-ray data, from the X-ray data we get the flux. From the X-ray data we get the temperature. These are relatively easy to measure. You will then, assuming you also know the distance, you will then be able to calculate the effective area of this bright radiating region. Then you need a little model. This is where a little bit of theory is needed to relate that area to the actual area of this dark region. But the models are fairly good. Of course, we don't have extra checks. The models we think should be good, so we use that, and you can measure the spin. There is one extra complication. A star is a sphere. So it's a circle whichever way you look at it. Disk is a plane thing. So depending on the inclination, there is an inclination correction you should do. What you measure is the projected area. What you want is the total area. So these are all, small details, but take a lot of effort to actually make it work. So this game has been played. And here is, for instance, a table. Most of this was actually done from our group at Harvard, my colleague McClintock, and numerous postdocs and students. So something like 10 stellar mass black holes for which masses have been measured. And now we have measured spin as well. And we get a whole series of values from 0.1, just practically 0, to practically spinning as fast as it can spin, 1. The whole range here. It's very interesting. We can kind of look at these numbers and try to make a lot of interesting sense out of this. Maybe in light of the LIGO discussion, I was talking with Ajith, I think this morning, some of these objects, SIGX1, LMCX1, M33X7, and maybe 1915, I'm not sure. Some of these objects will in the future become double black holes. We are fairly confident that they will become binary black holes. Presumably they will carry the spin along with them when they become the binary black holes. And then LIGO will see them merging. So when LIGO starts measuring a lot of spins, they should start seeing these values. And I think what we are finding is the sources that are potential future LIGO objects typically have large spins, according to our measurements. The low spins are not these objects. These are the low mass X-ray binaries. So Bala, that is something, as far as I know, so far LIGO is seeing no spin or small spin. If it continues, then I think something, either our method is wrong or LIGO's method is wrong or something is not working out. Okay, so let me continue on because I think time is running. Time scale for... No. It's cousins. So when in astronomy, we never think of this object actually doing something and us observing it. What we say is, objects like this are being created all the time. Today we are seeing this object as an X-ray binary, but something like SIGX1 must have existed, 6 billion years ago or whatever. It would have merged at that time. It would have looked like this. And when it merged, it might produce a LIGO signal, which LIGO will observe. So it's not the same object. Yes, LIGO is measuring spins. only in the population sense. So what I'm saying is, as a population, which is now a population of 4, okay? The population of 4 from X-ray binaries, the high-mass X-ray binaries, appear to have high spins. We have a population of 2 from LIGO. As far as I understand, they have somewhat small spins. Is this a problem? At 4 and 2, it's not a problem. But if we keep increasing and they keep increasing and there's a continuous mismatch, then something will have to be changed in our story. Okay, good. It's a good question. So let me, depending on the time, we'll go spin. Okay, if you have measured spin, okay? Better or worse, we have measured it. Some people have also measured spins for the supermassive black holes. We ourselves haven't done. There are more than one method, incidentally, for measuring spin. I only talked about our method. So they have used other methods. I'm not completely convinced those measurements are correct. So I haven't described it, plus I didn't have time. What is spin good for? Because as I said already, spin is this kind of new effect that comes in general relativity, which was not there in Newtonian physics. So what does it do? So to understand that, first let me talk about the astrophysics. Firstly, accretion disks, as I told you, radiate. How do they radiate? They radiate by converting potential energy into heat and radiation. And in fact, they do this very, very efficiently. In fact, for 1 gram of matter that falls into a black hole through an accretion disk, the amount of energy you get out in the form of radiation is much, much more than nuclear power. Okay, so this is the most efficient energy producer that we know in the universe. Second only to pair annihilation, where you get the full 100%. Okay, so in fact, these accretion disks, even though we think black hole is black hole-related accretion is extremely bright. And there is this statement that over the history of the universe, if you look at what all the black holes have done, they have produced as much radiation as all the stars in the universe have produced over their lifetimes, okay? It's an extremely powerful engine. Now, these engines have one more thing. It's not just radiation. They produce something called jets. There were already jets in some of the pictures I showed you earlier. If you remember, I had this disk and there was some lines sticking out along the axis. Observationally, we have these things called jets. So here is a very, very famous object, Cygnus A. So there's a big black hole here, right in the dot. This is real data, okay? This is radio image of Cygnus A. So there is a big, probably 10 to the 9 solar mass black hole here. It's been accreting for billions of years. From this black hole, there is this line that's sticking out, and you can just see the line on the other side. This is some coherent structure which is emanating from the black hole and traveling enormous distances. So just to give you a scale, the black hole is here. It's sitting in the middle of a galaxy. The galaxy size is about that much. And this jet is going about tens of times larger than the entire galaxy. So it starts from the black hole and goes about 9 orders of magnitude in distance before it finally dies. Okay, it just slams into the exterior, produces synchrotron radiation, etc. Now, from observations, you can estimate how much energy is flowing out in this beam. This beam has been doing its thing now for 1 billion years, okay? That's the age of the system, or maybe a few 100 million years. How much power is coming out in these beams? What one finds is it's a huge amount. It rivals the radiative output. So a black hole which is accreting gas produces this huge amount of radiation, and at least some of them also produce mechanical energy in the form of outflowing gas. And this outflowing gas can be moving at close to the speed of light. It's relativistic. We're not talking about one particle going at the speed of light. This is a whole column of fluid, magnetic field, particles, everything, all going close to the speed of light and going 100 times the size of a galaxy. I mean, it's just mind-boggling when you think about it. These are all, unbelievable until you actually see it. Okay, and we see it. We see many, many of these jets. These are just beautiful pictures which I pulled out of the web. They're all famous jet sources. Here is another famous jet source. This is so cute, I have to explain this to you. The concept of superluminal motion. So this is actually a stellar mass black hole, a famous object called 1915 plus 105. These are radio observations of this object. This is what it looked like on 18th March 1994, when they looked at it with a telescope. Then they went back and looked at it 9 days later, on 27th March 1994, and it kind of looked like that. It kind of got a little fatter. Then they went back 3rd April, and you could see that there were 2 blobs. 9th April, the blobs are moved further apart. 16th April, they moved further apart. So it's clear what happened. This black hole was accreting, and at that point, it decided to eject 2 blobs. One blob went in that direction, one blob went in this direction, and then they've just been moving apart. So far, so good. I mean, that's the beginnings of a jet. This thing will keep on going, and if there are more blobs, they'll all add up, and you'll get a jet, you might imagine. Now, the interesting thing is, you can now look at the rate at which this blob is moving in the sky. See, we have an image. We know what this is in angle, degrees or arc seconds or whatever. You know the rate at which it's moving apart. You know the distance to this object. So you can ask, what is the speed with which this blob is moving across the sky? It's greater than the speed of light, okay? This is why it's called superluminal. So these blobs appear to be moving apart at greater than the speed of light. By the time this observation was done, there was no surprise, because this is a phenomenon that had been known already for 30 years, or at least 25 years. It's been seen again and again. It's beautiful, simple physics. You don't even need relativity. It's going to be left as an exercise for the audience, but here's the trick. If I have a source of light which is moving, okay, and if it is moving towards you, not exactly, but slightly off at an angle, okay, so you're up there, so I've got a flashlight which is moving at some angle, and you are looking at this flashlight. Because it's moving slightly sideways, you will see it moving across in the sky. Because it's moving towards you, time gets compressed for you. You have to work this out, okay? So imagine that this flashlight sends out one pulse here, then goes here and emits another pulse. You will receive the 2 pulses much closer in time than they were emitted, because the thing is coming, it's chasing its own radiation. When you do all this calculation, what you'll find is, if the thing is moving non-relativistically, you get exactly the answer you normally expect. Namely, the velocity you measure is just the projected velocity. Whatever velocity it might be, the projection, sine theta, is what you measure. When you make it relativistic, so that this object is going at close to the speed of light, suddenly that speed of light comes in, and you can get apparent motion much greater than the speed of light. So in fact, the maximum you can get is something like gamma times c, where gamma is the Lorentz factor of this blob. So it's very interesting. If the blob is coming right towards you, you see nothing. Going right perpendicular, nothing much has happened. It's just like the ordinary case. But if it is slightly off angle, so that you're able to see some transverse motion, there is a sweet angle in which you can get up to gamma times greater. So that's what's going on here. This guy, the blobs are moving at a Lorentz factor of 2.6, velocity of 0.92 c. We can infer it directly from these observations. So a beautiful example of actual relativistic motion. Has been seen in many objects, okay? This is just a very nice example. Okay, here is what I was trying to lead up to. So we got these jets. And people have always wondered, what is it that makes these jets? Why should there be jets? You know, the black hole is attracting the gas and it's falling in. Where is the jet coming from? Why is it coming out? Why is it relativistic? Why is it so powerful? You know, these are all very good questions to ask. And for a long time, there has been this, I don't want to call it paradigm, let's just say a story, a hypothesis, that somehow spinning black holes are involved. That it's the spin of that central black hole that is somehow generating and keeping the jet going. So what I want to tell you here is, through computer simulations now, it looks like there is a lot of truth to this statement. Namely, we can simulate accretion on spinning black holes, make jets. On the computer, it happens beautifully. Does it really happen in nature? It's still an open question. I put a question mark. There is some evidence that it might be true, but there's a lot of evidence that it might not be true. So this time will tell. So let me start by just talking about the physics and the few computer results we have. And since we are running out of time, 5 minutes, Bala is a tough taskmaster. Yeah. So let's see how quickly we can go. The underlying concept behind all this is the idea that a spinning black hole has free energy. A non-spinning black hole is a useless object, okay? It only eats. You can send stuff in, and it's gone forever, until Hawking comes and gives you back Hawking radiation. But leaving that aside, a non-spinning black hole is just a one-way street. But a spinning black hole has got two sides to its personality. On one side, it eats. Happily, it's got an event horizon, it'll eat. But if you treat it right, this black hole can also give back energy. It has some amount of energy which is available to the external universe. This is what I call free energy. It goes all the way back to Penrose, 1969, who showed that the so-called ergosphere region of a spinning black hole has got special properties, and you can do things there to extract energy. So Penrose himself came up with one toy experiment where he said, if I had a spinning black hole and if I threw a particle into it and I did such and such, something, let's not worry about the details, I can get back the particle and it'll come back with more energy than I put in. How do you like it? I just drop a particle and it'll come out with a lot of energy. So you've got some energy out of the black hole. And if you keep on doing this, you are constantly extracting energy from the black hole. So that was Penrose's idea, and it's called the Penrose process. And many people have done beautiful work since then, including here in India, Dudley and company using magnetic fields. And yeah, so I'm not going to talk about that. Because as far as we can tell, those processes themselves are not very important in natural systems. That is to say, an accretion disk in nature is not likely to set up the precise geometry that Penrose wanted. But the idea is powerful. The idea of getting energy is a powerful one, and it appears that you could actually tap into that energy through magnetic fields. And this goes to papers from the 75, 77, Blanford and Snack in particular. So what I'm going to do now is I'm going to show you one movie just to show you, how this might happen. This is extremely toy movie, okay? There are much better simulations, but this brings out the concept. What I have here is a black hole. It's spinning around this axis. Okay. Outside this black hole, I've got a magnetic field line. So this field line goes to plus infinity, minus infinity. It's just a straight field line, embedded in some massless conducting fluid. Doesn't matter. It's just sitting there to start with. It's not rotating or orbiting or anything. It's got zero angular momentum. When I start the movie, this thing is going to start falling towards the black hole because of gravity. The gravitational pull is going to pull everything, the field line, the fluid around it, etc. Everything is going to come in towards the center, and you can see what happens. I'll just show you what happens, and then we'll discuss why it did that. So there's my field line coming in. Nothing special so far. Seems to be just going to go and fall into the horizon. This is the horizon, incidentally, this bright region. But it doesn't fall into the horizon. What it does is it comes to the front, swings around the black hole horizon, and just goes round and round and round. And what I want you to now focus on is, look at what's happening to the magnetic field line away from the black hole along the axis. You get a nice coiled spring-like pattern, and it's just moving away. And this will go on forever now. This field line will just keep on doing this, and it'll keep producing this pattern. So you should visualize this as the jet, okay? So I took one field line, and it kind of spontaneously produced this corkscrew with, actually you can show there's a flow of energy and angular momentum outward along the two axes. And that in kind of a just essentials is how we think a jet might be produced. So let me just explain very quickly what's going on here. I said this is a spinning black hole. Spinning black hole in general relativity have got the property, not spinning black hole, spinning anything, has the property that it will drag space-time. So space-time outside of this object knows that the object is spinning, and if you put something there, it wants to move in the same direction as the spin. In fact, it's unhappy to move in the other direction. So even if I put an object with zero angular momentum, it will come forward because that is the natural direction of the spin of the black hole. That's what's happening here. This is a zero angular momentum field line, but because of the spin, it gets wrapped up, produces my jet. One field line, 2004, very old work, and it's extremely toy. Slightly less toy models are now being run. So here is one simulation from Tchaikovsky. So this is just starting with a real disk of gas with magnetic field, and this is just to show you that it produces a jet. And there's a lot of interesting stuff here. Maybe I should kind of wrap up now, right? Okay. So let me not show this movie. I want to just make one final point and then I'll stop, okay? One final point. Okay, so let's say now we can run simulations. You want this simulation? Good, okay. Yeah, let's go for it, right. This is kind of state-of-the-art simulation, okay? Tchaikovsky. What we've got here is a black hole. So what we do now is you're trying to run this accretion disk physics on a computer. So you put a black hole, some mass, you start the system with a torus of gas around the black hole. So this black hole is spinning along this axis. There is a torus of gas which is orbiting around the black hole in the same direction. So this torus, this is a cross section, it's kind of like that. And it is axisymmetric to start with. These are some magnetic field lines here. Weak magnetic field lines to start the experiment. Important thing, there is no field line that goes from infinity to infinity. It's all inside this torus. So the point of this experiment is to show that this guy will spontaneously set up what it needs to make a jet. So just watch the black field lines as I run the movie. These are all very ambitious experiments. They take enormous numbers of CPU hours. But watch the field lines. This is all doing its stuff. The gas is accreting. The field line is coming in. But watch what happens to this guy. Then it kind of shoots off. Next field line comes, it shoots off. So this guy, even though it started with a fairly compact magnetic field, spontaneously, the way the physics works, it generates by itself a bundle of field lines which are really extending to very large distance around the spinning black hole. Each of these field lines, these are actually rotating. I can't show it in this projection. So each of these is a corkscrew. All of these field lines are doing what I showed in the previous movie, and there's a huge amount of power going out nicely along the two poles. Very powerful jet. This was a particular simulation with a spin of 0.99 or some very large spin. I won't show more of this because there's a lot of astrophysics, but you don't need to know all that. I just wanted to make one point on this simulation, and then we will stop. Something about efficiency. So I already told you that accretion is an efficient way of producing energy. In this case, radiation, usually. So here is the typical numbers that people talk about. If I keep adding mass to a black hole at some rate, let us say 100 grams of mass fall in. Typically what an accretion disk will do around a black hole, it will produce 10 c² worth of energy in the form of radiation. That's what will come out. This is what we observe, quasars and X-ray binaries, etc. The remaining 90 falls into the black hole. So the black hole becomes heavier. 100 units of mass go in. The black hole becomes heavier by 90 units because 10 units were converted to energy which came back to infinity. This is great. This is what all of our accretion systems are doing. And we are very happy that we got 10% because You don't get 10% from even nuclear reactions. This is a very, very high efficiency phenomenon. Now let me talk about this simulation. I think this guy has lost its... If you go and look at that simulation that Tchaikovsky did, since it's a simulation, you can calculate everything, right? You got data, 1 terabyte or whatever, 50 gigabytes of data, and you can look at it and make any calculation you want. So you know how much mass you dropped into the black hole, you know how much energy came out in the jet, and that guy had this amazing result that 100 grams of mass fell in, 140 c squared of mechanical energy came out in the jet. Just amazing, right? Looks like a free lunch here. How can you just drop 100 and get 140? Something must be wrong. In fact, nothing is wrong. It's just Penrose. Penrose is helping you. Basically, what's happening is, I'll show it in the next picture. You dropped in 100, the black hole in its own infinite kindness gave an extra 40, and 140 came out in the form of a jet. So it's beautiful. So this, actually the black hole is eating gas, believe it or not. 100 protons will go in, but 140 proton mass c squared of energy comes out. And the black hole will actually get lighter. So the black hole is constantly eating gas and becoming lighter all the time. It's beautiful, I tell you. I wish I were a black hole and I could control. Yeah. But at the end of the day, it is Penrose, okay? The concept here is very simple. We are tapping into the spin energy, and you can see that in the simulation. In the simulation, you can see energy is flowing out of the black hole, angular momentum is going out of the black hole. The black hole is actually spinning down, so it can't go on forever, okay? If you try to continue forever, the black hole will become non-spinning, and then it's useless. It can only eat after that. Okay, so this is beautiful. I think on the computer at least, we think we can see Penrose in operation through magnetic fields. And the rest of my talk I will just leave out, because what I wanted to talk about next was all stuff I'm going to say next week about the Event Horizon Telescope. So let's leave that aside. I'll just finish with a summary. So black hole is one of these concepts where the theorists were way ahead of experimenters. Decades ahead, okay? So it was there for years and years, and everybody thought it was just a toy. And then suddenly we found that, in fact, this thing is real. Not just real, it's a very, very large population in the universe. 2 kinds of black holes. This is something that has been suspected for long. Now I think more and more people are warming up to the idea that these relativistic jets probably are being powered by some form of Penrose process, magnetically driven. This is the topic that I didn't have time to talk about, but it's just as well, because I'll talk about this next week. So it's a beautiful field, just with electromagnetic radiation, and now it's become even more beautiful thanks to gravitational waves, and I guess we'll hear about that next.
Make it pretty simple. Thanks, Ramesh. So a few questions.
Hi, very nice talk. So at one time I briefly remembered there was some doubt about the torque at the inner edge of the accretion disk if it is particularly magnetically coupled. Is that issue sort of sorted out, or?
Depends whom you ask. So let me tell you, the question has to do with this accretion disk, which comes down to the ISCO. And I told you that inside the ISCO, gas falls into the black hole, right? So there are certain old models, going back to Shakura and Sunyaev, Novikov and Thorne, etc., where they have 1D models of what the properties of the disk are outside the ISCO. And when they do these models, they have to put a boundary condition at the ISCO. And so they made a certain zero torque boundary condition, seemed natural, and they worked out the model according to that. Now, when we try to measure the spin, remember, we are using some model of the accretion disk, how the brightness varies with distance, etc., to get the area of the hole in the middle, all of that stuff. There is a bit of a model involved there. And so there was this legitimate question, should we believe the model? Because it's based on one everything is very, very solid, but there's one assumption, a boundary condition. So there was an issue. People were worried whether it's okay or not. So we did some computer simulations of those kinds of systems. The beauty about a computer simulation is you don't have to put a boundary condition. You just give it some initial conditions and it evolves according to equations. It'll do whatever it wants to do, okay? Then you can go in and ask, what did it actually do at the ISCO? So when we did the simulations, what we found was the deviations from that assumed boundary condition are very small, just a few %. So it didn't affect any of our measurements. But there was another group that did the same work, and they claimed that it's a much larger effect. So you're asking whether it's been resolved. As far as I'm concerned, I believe my result. But this is one of those things where we have each moved on, and it's still there. I think it's what we said is right, that it doesn't make a big difference, yeah.
Sir, in the last simulation that we saw, you showed us how field lines moved in the presence of a black hole. So what were those field lines exactly? Were they X-ray field lines or what?
These are just magnetic field lines that are impregnated in the gas. Okay. Everywhere in the universe, wherever you see gas, there is always some magnetic field. The universe is full of magnetic fields. Just random fields that have been created by various means. You know, the Earth has a magnetic field, the Sun has a magnetic field. You can't look at anything without seeing magnetic fields. So in that simulation, what we are saying is there is some magnetic field in this gas. Not much, just a little bit. But the accretion will take that little bit of field and nicely order it, strengthen it, and make it just right to produce a powerful jet. So that was the point I was trying to make there, yeah. So we put the field in by hand, okay? But it's reasonable because nature does have magnetic fields.
So in the summary slide, there are two distinct populations of black holes, right? So is it possible to have intermediate black holes, or is there a theoretical constraint, or is it just lack of observation?
Beautiful question. So there is a whole field of study called intermediate mass black holes. You use the word intermediate. You probably work in this field, yeah. So, so the intermediate mass black holes are black holes, say, with their typical mass at, say, 1,000 or 10,000 masses with some distribution. Question is, do they exist in the universe? Which you can answer by looking at observations. Try to see some object which you cannot explain with the traditional black holes, for which you need an intermediate mass. And people have found some objects, so-called ultra-luminous X-ray sources, for which it seems an intermediate mass black hole might be a good idea. Nothing is foolproof. For me, a mass measurement is foolproof only when it's done through this kind of dynamical measurement, and this hasn't been done. Then the question is, theoretically, can we form intermediate mass black holes? We don't have a really good way to do it. So the story I can tell you is, we have a very good idea how to make these black holes. We don't have a very good idea how these supermassive black holes come about. We just wave our hands and say it's something part and parcel of a galaxy. A galaxy is a big object. When it forms, for some reason, a fraction of its mass becomes a big black hole in the middle. But because it's associated with the galaxy, this, even though it's a small fraction, it's still a very big black hole. We don't have an equivalent scenario for producing intermediate mass black holes. So people try to do it by merging lots of smaller black holes. People try to do it by starting with some first generation of stars, which might be very massive. Maybe there was a 5,000 solar mass star early in the universe. Maybe it collapsed. These are all very, very speculative. but it's a search that's still going on.
So
We'll have two questions.
inside the ISCO, there isn't any stable orbit for sure, but the stuff might come out of the ISCO, right? It doesn't have to fall inside, right?
In these,
The photons, everything, depending on the initial phi dot and everything, it might come. When you said it falls in radially or...
in this particular problem I was talking about, the gas is already bound by the time it reaches the ISCO. It doesn't have enough energy to come back to infinity. It has only one place to go, into the black hole. You can think of other scenarios where you can hit the ISCO and still have enough energy to escape to infinity, but that doesn't happen in the actual accretion disks. The point you make about the photon orbit is all very good, yeah, but that is not directly relevant here.
And so your ISCO was going up to 1 GM by hour. Okay, sure.
Yes. Yes, absolutely. Absolutely. It's a beautiful question. So let's take the extreme example. Okay? Let's say I have a black hole which is spinning at the maximum rate allowed. This is this A equal to 1. Let's say I put an accretion disk which is in orbit in the same direction. Then the ISCO is at 1 GM over c squared. That's what I showed in my plot. So it's the closest you can get. Let's take the same black hole, put an accretion disk that's going around in the other direction. This guy will have its ISCO at 9 GM over c squared. So it makes a huge difference whether you're co-rotating or counter-rotating. And just as an extra tidbit, I showed you a table of 10 objects for which we have measured spin. So in those objects, not only can we measure spin, we can also tell you whether the disk was going in the same direction as the black hole or the opposite. All 10 of them is going in the same direction. So they all happen to be co-rotating. And it's astronomically, it's quite plausible. But we could have discovered, if it was going the other way, we would have been able to discover it. It wasn't there.
So can you measure the angular moment of the black hole?
When you measure the spin,
Yeah.
A, it's the equivalent to measuring the angular momentum. So there's a simple relation. I'm not sure about all the powers of C, but J is equal to this A star. Is that about right? Something like that, okay? I'll put a question mark here. But basically, if you measure the spin parameter and you already know the mass, it tells you what is the angular momentum of the black hole. Yeah, so these are actually considered to be equivalent. This is a dimensionless number. This is actual angular momentum. It's got dimensions of angular momentum.